Hey everyone, welcome back. This is lesson 3 in our unit thermochemistry. And today we're going to be focusing on part 1 of heat calculations, the Mcat equation. So in the last video, we talked about heating and cooling curves in a lot of detail. But this time we're going to focus on heat calculations, and it's Q equals MC delta T. I think the delta kind of looks like an A, so that's why I refer to it as the Mcat equation. So before we kind of jump into that, let's kind of take a step back and talk about energy. So far this year, we've talked about the law of conservation of energy, charge, mass, all those three things. Basically, what they say is that you can't just magically create or destroy stuff in a reaction. It just kind of shifts things, or shifts types. It's a better word. So when we're talking about energy, there are 6 different types of energy. So we have chemical, electrical, mechanical, nuclear, heat and thermal, electromagnetic radiation. But this unit, we're focusing on that heat and thermal energy. So before we again jump into the equation, there's a few vocab words we need to discuss. So first is exothermic. And so exothermic means energy is being given off in a reaction from the system. So the system is a fancy way of saying the thing we're looking at to the surroundings, which is the outside or everything else. It's a better way of putting it. And so the thing or the system becomes colder. So if you think of like an exoskeleton in those, in some insects, it's on the outside. Energy in an exothermic reaction is given off. It is, I like the word released, a little bit better. Okay. So if you're releasing energy, the thing itself, the system becomes cooler because energy is being given off. In an endothermic reaction, endo is the exact opposite. So now energy is being absorbed, again, by the system, which is our thing, from the surroundings, so on the outside. And it becomes hotter. If you absorb energy, you absorb heat, you do become hotter. And so the last thing is specific heat. So specific heat is the amount of heat it takes to raise the temperature of 1 gram of the substance 1 degree. So if we're looking at water, for example, the specific heat for water is 4.18 joules per gram degree Celsius. And so what that means, if you had 1 gram of water, so fun fact, 1 gram of water is equal to 1 milliliter of water, so not that much. It takes 4.18 joules, and so J, word joules, so we're going to use that word a lot, is our, so I spelled that wrong, is our unit of energy. So it takes 4.18 joules to raise 1 gram, so 1 milliliter of water 1 degree. So relatively speaking, water has a pretty high specific heat value. And so if we're talking about metals, the specific heat values for metals are generally a lot lower. And so you kind of already know this. If you were to put, something metal outside and a glass of water outside, given the same temperature, the metal would heat up a lot faster because it's easier for the metal to heat up faster because of that lower specific heat. It does not take as much energy for the metal to raise the temperature. Okay, so this value is something you do need to know, but it is on table B, so you don't need to memorize it. You just need to know that it exists and where to find it. So here is our equation. Again, I like to call it the Mcat equation. And so let's take a deeper look into what all these things mean. And so Q represents the heat, and that is our joules. If Q is positive, that's endothermic, meaning our energy is absorbed. If you have a Q that is negative, that's exothermic, so your energy is released. M is mass. C is your specific heat capacity. And delta T is your change in temperature. And so this triangle is delta, and so it shows you the change of it, so how much temperature changed, and you can figure that out by doing the final temperature and the initial temperature. So in an equation, you'll be given everything you need to solve for that one missing variable. So if it doesn't give you everything except that one missing variable, they give you enough to either tell you what substance you're using so you know to use the reference table, or for example, they don't give you delta T, but they give you those two. And so we're going to jump into questions that show you this. But again, before we do that, let's just kind of relate this back to heating and cooling curves. So the Amcad equation is only used when temperature is changing. And to remember, here is temp, here is time. And so in these slanty sections, the temperature is changing. And so this equation only works when you have that change in temperature. So if you try to do it on those flat sections, your temperature is not changing, and so your delta T would be 0, and then if you plugged 0 into your equation, it wouldn't make any sense because you'd have an answer of 0. So it only works on those slanted lines, which is when your object is being heated or cooled, if this was a cooling curve, when it's all solid or all liquid or all gas. We'll talk about what happens on the other two lines later. So here is table B, like I said before. So just for today, we're going to focus on the specific heat of water. We'll talk about the other two values next time. But something else I want to mention is the unit. So here you see it as grams per degree Kelvin. You can also see it as degrees Celsius. For this unit, the temperature unit doesn't matter. So what that means is if the question gives it to you in Celsius, fantastic. If the question gives it to you in Kelvin, cool. You do not need to convert at all. So you need a temperature unit, but it doesn't matter which one you are given, because Celsius and Kelvin, they're on the same kind of scale. So a 5-degree change in Celsius is the same as a 5-degree change in Kelvin. They're just Kelvin is much, much, much lower on the scale, but it's the same scale. Okay. So let's jump into one of these questions. And so whenever we jump into math, or any equation really, I like to write my equation down and list out all of our stuff. Okay, so the question is how many kilojoules? And so that is what we're looking for. Kilojoules, joules, that's our Q, are absorbed when we have 1,000 grams. So 1,000 grams is our mass, is heated from 18 to 85 degrees. Now, at this point, we're technically only really given mass, but remember, we know delta T is T final minus T initial, and so our final temperature is 85, our initial is 18, so our delta T, our change in temperature, is 85 minus 18, which is 67 degrees Celsius. And so now we have that, but we're still not given C. But the clue in the question said we were given water. So according to table B, remember, the specific heat capacity for water is 4.18. So we can add that right now. So 4.18, and the unit is G over that. So that comes from the reference table. So now that we have everything we need, let's plug in. So Q equals our M, 1,000 grams, times 4.18 joules over grams degrees Celsius, times our delta T, which is 67 degrees. And so now you'll notice grams cancel and degrees Celsius cancel, leaving us with J, or joules, and that's our unit of Q. And so when we plug this in, we get 1,000 times 4.18 times 67, which gives us 280,060 J. Now, the question, though, asks us for kilojoules, and so 1 kilojoule is the same as 1,000 joules. So all we have to do is move our decimal spot over 3 spots. So Q is 280 kilojoules. And that is it. Now, when we talk about this unit specifically, if you see multiple choice questions, they love to use significant figures. So if your answer doesn't match exactly, it's because significant figures are used. And that's why we wrote only 280, because our answer can only have 2 significant figures, because 67 has 2 significant figures. Now, last part of this question is, this is an endothermic or exothermic? And so we can say it's endothermic because heat is absorbed. Now we know that because first it says absorbed, but also our our Q value is positive. Remember, positive Q equals endo. Okay, let's jump into number 2. So again, we have our equation. We're going to list out what we have. Q, M, C, delta T, TF, TI. Okay. So the temperature of a 95.5 gram of copper increases from 25 to 48 degrees. So we're starting at 25, ending at 48. So our delta T is 48 minus 25 equals 23 degrees Celsius. And absorbs 849 joules. 849 joules of heat. What is the specific heat? So here we're given everything except specific heat, and it's okay because copper has a much lower, it has, you have to find it because it's not on the reference table. That's okay, we're given everything else. So if we plug in, we know 849J equals M, which is 95.5 grams, equals RC, times RC times delta T, which is 23 degrees Celsius. And so if we want to get C by itself, we can do 95.5 grams times 23 degrees C. So you get 90, divide both sides by that. 23 degrees C, so that cancels. And so, grab a different color, get 849J over 95.5 G times 23 degrees Celsius equals C. And so when you plug that into your calculator, and so let's just do it this way, 849. So 849 divided by 95.5 times 23 is 2196.5. And so 849 divided by 2196.5 equals 0.3865, blah, 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 blah. We're going to leave it as 0.39. And then our unit is, if we look over here, we used all these numbers, but we have the unit J divided by G times C. So J divided by G times C, and that is our unit for specific heat. Okay, so in this question, we're looking for if it's endo or exothermic. It's endothermic because first we know our Q is positive. It also says heat is absorbed, so we can fill it out like that. Okay, last question is number 3. So again, like always, let's start off with our equation. Q equals M equals C equals delta T equals TF TI. Okay. 300 grams of ethanol, so that is our mass, at 10 degrees, so that is our initial, is heated with 14640 joules of energy, so 14640 J. What is the final temperature? So we're looking for that. The specific heat is 2.44 J over GC. Now, we're looking for TF. But in order to find, we're given the initial temperature, but before we're able to find that, we have to find delta T first. So this is the hardest type of question that you will see on this. So let's do this one a bit differently, just to kind of give you multiple ways you can be doing things. So remember, our equation is Q equals mc delta T. And so if you liked what we did last time, plugging in, then solving for C, that's cool. But let's solve for delta T before we start. And so if we want to get delta T by itself, it's like that. You divide both sides by mc. So delta T is Q over mc. And so now we've already manipulated our equation, so we can just kind of plug stuff in. And so with that method, and again, whichever method you like better, delta T equals, our Q is 14640. I'm just going to ignore my units now just so it doesn't get too messy. Our mass is 300, and our specific heat is 2.44. And so I like to do each step, 14640 divided by 300 times 2.44 is 732. And so 14640 divided by 732 equals 20. So our delta T is 20 degrees. And so we're not done yet because it's asking us for the final temperature. But remember that delta T is our T final minus our T initial. And so if we're going to find our delta final, add Ti, or your initial, to both sides. So your final temperature is delta T plus your initial temperature. So TF is our delta T, which is 20, plus our initial temperature, which is 10. 20 plus 10 equals 30 degrees Celsius, and that is your final temperature. So this is the hardest type of question you'll see in this unit, or in this topic, because they make you find the variable and then use an extra little step. Now, again, good practice, we're looking at an endothermic. Remember, our Q is positive, meaning heat is absorbed. You'll see other examples where it's exothermic and that negative Q value. But for right now, we have been endo because energy has been absorbed. And so that's pretty much it for this unit, or not this unit, this video. Next time we'll talk about the heat of vaporization and the heat of fusion equations. But that is it. Have a wonderful day.